So, good morning, everyone. So, last class we had discussed about basic probability, introduction to basic probability, and certain terms related to probability, and we had defined the a priori definition or the mathematical definition of probability. So, the mathematical definition of probability was defined as P of A as what? Number of favorable outcomes divided by total number of outcomes. So in this way we had defined the priori definition or the mathematical definition of probability. So in this case I had mentioned that one of the most important assumptions which we make during this a priori probability is that the cases, that is the event which we are taking, should be equally likely, and I have asked you to underline that also, equally likely cases only. So here we mention what are the limitations of next we mention what are the limitations of this, what are the limitations of what we say, the classical definition or the mathematical definition. What are its limitations? One of the most limitation is this one only. In most of the time, in most of the experiments, the trials need not be equally likely. For example, if you toss a coin, here you see that either it will result in head or tail. But if it is a biased coin means probability of getting a particular event, that is either head or either tail. Probability of getting head is always greater than probability of getting tail, or vice versa. Then we say that the coin is biased. Okay, then we say that the coin is biased. So in these situations what happens is that in these situations we see that this classical definition of probability does not hold. So it holds only when probability of head equal to probability of tail. So if this condition, that is the condition of equally likely, is satisfied, then only we can find out the probability using the classical definition. So in most of the case in probability we see that there will be some biasness or some consequences in the environment under the certain environmental condition. If we do a random experiment, then it will be correspondingly making changes in its results. So we cannot say that every experiment will be equally likely, and moreover in most of the experiments we see that most of the experiments are not equally likely. Okay, this is one of the example of not being an equally likely case. Then another demerit is that if the exhaustive number of outcomes of a random experiment is infinite or unknown. So this definition fails when the exhaustive number of outcomes of a random experiment is infinite or unknown. By this I mean that suppose I am interested in studying, if I am for example, if I throw a coin, if I throw a coin, suppose that I throw a coin is tossed, then the sample space is head or tail. But uh, I am I am interested in studying whether I will be getting a first head. So my experiment in this is the sample space, but my experiment is getting a head. Okay, so at this time point it may be, so in first experiment I can get a head, otherwise in second experiment I can get a head, or in third experiment I can get a head. Simultaneously I may not get head also. Okay, so here we see that this is infinite. Okay, this is infinite. Here the random experiment is infinite. I'm not sure at which of the trials I will get a head. Okay, so at this point the sample space is infinite, so at this point of time we cannot use the classical probability. Cannot be used. Okay, another example is that when a die is thrown, okay, then suppose my interest is getting 6. So sample space will be, first time I will get 1, second time I will get 2, third throw I will get 3, fourth throw I will get 2, fifth throw I will get 5. So I don't know at what point I will get 6. So this is infinite, and in these cases too our classical definition fails. These are some of the demerits of classical definition. Okay, and not demerits, it is its limitations. It is limitations of classical definition. Okay, classical definition of probability. So in order to overcome these problems, what we have is that, and moreover, suppose in this case, suppose that in classical definition, suppose that I throw a die. Okay, throw a die, then for 5 times, what I get is that I get a sample space of head, tail. So yesterday's example itself, so I get the probability as head, tail. So here we see that the probability of head is 3/5, because total number of favorable cases by total number of events, so it is 3/5. And probability of tail is 2/5. Okay, we know that total probability is 1, so probability of t will be nothing but 1 minus probability of head, because there are only 2 events. Okay, so we can write like this also. So what happens here is that in classical probability we have to do this experiment. We have to make sure that if this situation is okay. Suppose that if I consider the throwing of die in 10 times, so here we may also obtain that it will be h t h like this. If I have 10, then suppose that 10. Okay, so here we say that probability of h is 8/10, and probability of tail is 2/10. Okay, so what happens in this case is that we have to increase the number of trials. So here comes the concept of frequency definition of probability. Here comes the definition of frequency definition of probability. So here what we have to do is we have to as we increase the sample size more and more, the precision of our probability becomes larger. Okay, here we had only 5 case, here we had 10. If we continuously go up to 100 or 500 trials, then only we will come to know how far or how good is our probability, because as the sample size increases, then only we can say how much good is our estimate or something. Okay. So we will write the frequency definition of probability as frequency definition of probability. Frequency definition of probability. Or it is also known as empirical definition of probability or empirical probability. It is also known as empirical probability. Okay. So we'll write, if an experiment is performed repeatedly under essentially homogeneous condition, essentially homogeneous and identical condition, then the limiting value of the ratio of the number of times the event occurs to number of trials as the number of trials becomes large is called the probability of happening the event. Assuming that the limit is finite and unique. So here we see that if an experiment is performed repeatedly under essential homogeneous and identical condition, the limiting value of the ratio of number of times the event occurs to number of trials as the number of trials becomes large is the probability of happening of an event, assuming the limit is finite. So as I have said, in this case I have this classical case has to be continuously done under certain conditions, under the same identical condition, infinitely large times. That is, if we do this 100 to 200 or to 500 times, then we can say that this becomes the basic definition of empirical probability. So here we can say that symbolically if n is the trial and he happens n times, sorry, m times e happened m times, then the probability of e is, then the probability of e is nothing but limit, this n should be very large, so I say that n tends to infinity. So this n should be very large, it should be greater than 500 or it should be greater than 300, like that. So it is nothing. So same idea is m by n, number of favorable outcomes by total number of outcome. The idea is same, but here we make another approximation, which is the sample size should be very large. So then only we can say that this converges in probability. We say that it converges in probability. Okay, then only we can say. So this is the basic definition of frequency definition of probability, or empirical definition of probability. Okay, so I think that the idea is very much clear to you. Then next we can do one thing. This is the idea behind frequency definition of probability. So we had seen two types of probability. First one is the classical definition of probability. Okay, another one is the frequency definition or empirical definition of probability. So which is somewhat same. For this we can say that it repeats n times or infinity times. We can say that it repeats infinity times. Okay, so another measure of probability or another definition of probability is given by axiomatic definition of probability, which is the unique definition of probability, or which is the among these three, which is the best definition of probability. So this we will studying after some after doing some numerical problems associated with these types of probability. And so now we will look upon the limitations of as an example of what we say, free empirical definition of probability. You can write it as a coin is tossed many times. A coin is tossed many times. Suppose that the coin is tossed 10 to 100 times, then the probability becomes like this. If the coin is tossed 100 times, then probability of head will be almost equal to, so say 60 by 100, then probability of tail will be nothing but it will be what, 40 by 100. Okay, then this we can repeat 600,000, 400,000, like this. So if we repeat this infinite number of times, then only we can say how much sure we can be about this probability. Okay, this is the main idea behind a fiduciary probability or empirical probability or frequency definition of probability. Now we look upon the limitations of this probability. Okay, limitations of empirical probability. So one of the limitation is that we see that we had defined a fiduciary probability as limit n tends to infinity m by n. So here we had seen that here there is a limit. So one of the demerit is that the limit in empirical probability may not attain a unique value. Okay, this is one of the demerits. For example, if you consider a coin is tossed 10 times, then you may get probability of E as getting head as 6 by 10. So if the coin is tossed 12 times, then you may get probability of head as 8 by 12. If the coin is tossed 15 times, you may get it as 9 by 15. Like this you may get. So every value differs. Okay, so if you consider these values limit as this value differs very much as this limit gets on increasing. So as the limit gets on increasing, the limit in empirical probability may not attain a unique value. It does not have a unique value, but it converges to a particular value. But it only converges to a particular value. So here we see that in most of the case this increases or this decreases, and it does not have a particular value or a unique value. This is one of the limitation of empirical probability. So one asked you what is the probability of getting a head, you cannot say that it will be a particular value, whereas you can only say that it will be having or it converges to a particular value. You can only say that it will converge to a particular value rather than saying that its probability is 0.5 or 0.6. We cannot say it in particular way. Okay, I think that the idea is very much clear to you. This is one of the limitation of empirical probability. Okay, another demerit of empirical probability is that if the experiment is repeated large number of times, if the experiment is repeated large number of times, the experimental condition may not remain identical and homogeneous. So by this I mean that if we do for 10 repeated samples we can find an identical condition. So as the number of observation gets increasing, so the property of uniqueness in each trial become lost. So the condition of homogeneity or the condition of homogeneity cannot be maintained as the time passes. Okay, this is one of the demerits of empirical definition of probability. Okay, so these are some of the basic ideas regarding the two types of probability. One is the classical definition of probability and another one is the empirical definition of probability. Okay, it's the basic idea. So we will do one thing, we will do some questions, some numerical questions to these two types of probability. Okay, suppose so let us do some questions, numerical questions to this probability. So first question is two unbiased dice are thrown. Two unbiased dice are thrown. Find the probability that both the die show the same number. Okay, second one, the first die shows 6. The first die shows 6. Okay, this is the question. Two unbiased dice are thrown. Find the probability that both the die show the same number and the first die shows 6. So here we see that okay, here we see that here the cases are equally likely. Here the cases are equally likely. So uh, we adopt what we say, classical definition of probability. Classical definition of probability. Okay, so first is to understand which type of definition should we use. So if a die is thrown, so now next step is we have to make the sample space. Okay, what should be its sample space? So a die is thrown how much times? 2 times. Okay, sorry, the die is thrown 2 times. So what happens is that its outcome may be 1 1 1 2 1 3 1 4 1 5 1 6. Similarly 2 1 2 2 2 3, like this it continues. One more thing you have to understand, one thing, that 2 unwasted dice are thrown and a die is thrown twice. In both of the cases the sample space remains the same. So if a coin is tossed 2 times and a coin is tossed 2 times and 2 coins are tossed simultaneously, then too the sample space remains the same. Okay, 3 1 3 2. So this is the sample space. Okay, so here how much events are there? Total number of events is, so there are 36. Okay, there are 36 number of events. Okay, then so we look, there are 36 number of cases. So it is such that how can we find out total number of cases? If there are while throwing a die, there are single die, there are 6 chances. So 6 chances is repeated 2 times, so 6 square is 36. So if a coin is tossed, for example, if coin is tossed 2 times, then head and tail, so it is repeated 2 times, then there should be 4. It is correct. Head head, head tail, tail head, tail tail. These are the 4. Like this we can find out for any number of combinations. Okay, so there are 36 number of combinations in each trials. So in this way also we can find out how much number of trials are there. Okay, so in the present question we had to find out what both the die show the same number. Okay, both the die shows the same number. So both the die shows the same number. So first one, probability that E1, suppose E1 is both the die show same number. Then probability of E1 is number of favorable cases by total number of cases. So here both the die show same number. What are the both the die show same number? 1 1. So here how much combinations are there? 1 1, 2 2, 3 3, 4 4, 5 5, 6 6 divided by 36, total number of cases. So 6 by 36 or 1 by 6 is the answer. Okay, very much clear. I think that this idea is very much clear to you. Okay, so these are the number of cases, favorable cases by total number of cases. The basic definition of classical definition of probability. Okay, next one is we have to find out the first die shown 6. The first, so I define this as E2, where which is the first die shown is 6. In which we look into the sample space in which the first, so here 1 2 3 4 5 6, so these 6 cases. Okay, which are the cases? 6 1 favorable cases are 6 1, 6 2, 6 3, 6 4, 6 5, 6 6. These are the favorable cases, and there are 6 favorable cases divided by total number of item, which is 36. This 2, the probability is same, probability of E2. So there are favorable cases are this one, double cases or this one. So we get the probability of 1 by 6. Now I add one more question, that is the total number on the total number on the die is 8. Total number on the die is 8. So the total number of die on the is. So here I write this, I call it as E3. So the favorable cases. So what are the favorable cases? Total number on the die is 8. So if I have to get 8, what are the combinations? 6 plus 1, we get only 7. So we cannot take anything from the first row. So I take 6 plus 2, 8. Okay, then 5 plus 3, 4 plus 4, 3 5, 6 2. So there are favorable cases are 2 6. Okay, 2 6, then 2 6, then 3 5, 4 4, 5 3, then 6 2. These are the cases. Is there any other case which gives total number 8? No. Okay, so probability of E3 is nothing but total number of cases 5, number of favorable cases is 5, and total number of cases 36. 5 by 36 is the answer. Okay, now I take another example where total number on the die is greater than particular value, say 8, greater than 8. So here too I have to find out number of favorable cases. Here what are the favorable cases? If we look into this, 6 and 2 is greater than 8, 3 and 1 it is not greater than 8, 5 3. So 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. Okay, so the favorable cases are 2 6, 2 6 2 6 3 5 3 6 3 5 3 6 4 4 4 5 4 6 5 3 5 4 5 5 5 6 6 2 6 3 6 4 6 5 6 6. So there are 15 cases, favorable cases. So there are total number of cases. Probability of E4 equal to number of favorable cases, there are 15. Total number of cases, there are 36. So this is the probability. Okay, this is the probability. Then E. The total number on the die is 13. Total number on the die is 13. So if we add any two numbers, then it should get 13. So if we look at any, so here you see 6 plus 6, the maximum will be 12. So we cannot get any number which is 13. So number of favorable cases is equal to 0. So probability of E5 is number of favorable cases 0 by total number of cases 36, which is 0. So probability of E5 equal to 0. Probability of E5 is 0. Okay. Another example we can total number on die is less than 5. So what are the cases here? Number of favorable cases here less than 5 means that 2 1 1 1 2 1 3 4 plus 1, this is inclusive, 5 is inclusive, so I exclude 5, so we have only 3. Okay, 1 1 1 2 1 3. Okay, I include that 5 is less than, it is strictly less than. Okay, suppose that this is strictly less than, so I exclude it. Then from second row we have 2 1 2 2. In third row I have 3 1. So these are the total number of favorable cases. So my probability E6 will be number of cases 1 2 3 4 5 6. 6 by 36. 1 by 6 is the answer for this question. So this is the basic example of an axiomatic probability definition. Okay. Now we'll look upon more number of examples, similar examples. Okay. So here we look upon another example. what question, another question 2. Okay, what is the chance that a leap year selected at random will contain 53 Sundays. The question is, what is the chance that a leap year selected at random will contain 53 Sundays? So we know that so in a leap year there will be how much days? There will be total number of days in a leap year is 366 days. Okay, so if we divide it by 7 is a Sunday, Monday, Tuesday, like that, 7 days. So we will have remaining 2 days. So how much combination we can make, like that we have to think. So it can be a Sunday and a Monday in a leap year, or it can be Monday and Tuesday, or it can be Tuesday or Wednesday, and it can be Wednesday and Thursday, or it can be Thursday and Friday. One is Friday or Saturday, and Friday and Saturday, and last one is Saturday and Sunday. Okay, these are some of the parametric combinations: Sunday and Monday, Monday and Tuesday, Tuesday and Wednesday, Wednesday and Thursday, Thursday and Friday, Friday and Saturday, Saturday and Sunday. So there will be 2 days left if we divide by 7. So this is the parametric combination. So here we have asked that how much it will contain 53 Sundays. So here if we divide it by 7, we will get 52 plus 2 days extras. Okay, so if we have നമുക്ക് 53 വേണമെന്നുണ്ടെങ്കിൽ it should be Sunday and Monday combination or Sunday and Saturday combination. Okay, so total number of favorable cases 2 divided by total number of cases 7. So the required probability is 2/7. Okay, this is the basic idea behind a leap year question. Okay, നിങ്ങളൊന്ന് നോക്കിയാൽ മതി, അന്നേരം മനസ്സിലാവും. ഇപ്പം 52 × 7 കൂട്ടിക്കഴിഞ്ഞാൽ 7 2s are 14, 35, 36, 364 വരും. അപ്പോൾ 366 വരണ്ടേ, അപ്പാണ് 2 ഡേയ്സും കൂടി ആഡ് ചെയ്താൽ മതി. അപ്പോൾ ഈ 2 ഡേൻ്റെ കോമ്പിനേഷൻ എന്തെല്ലാം വരാമെന്ന് ഞാൻ പറഞ്ഞത്, സൺഡേ മൺഡേ, മൺഡേ ട്യൂസ്ഡേ, ട്യൂസ്ഡേ വെനസ്ഡേ, വെനസ്ഡേ തേഴ്സ്ഡേ, ഇങ്ങനെ വരാം. അതിൽ നിന്ന് ഇതാണ് നമ്മുടെ ടോട്ടൽ നമ്പർ കേസ്. അതിൽ നിന്ന് ഫേവറബിൾ കേസ് എന്താണ്, 53 സൺഡേ വരണമെന്നുണ്ടെങ്കിൽ ഇങ്ങനെ വരണം, ഇങ്ങനെ വരണം, ഇങ്ങനെ വരണം, ഇങ്ങനെ വരണം. ഇനി എൻ്റെ അടുത്ത ക്വസ്റ്റ്യൻ, ഇഫ് ലീപ്പ് ഇയർ സെലക്റ്റഡ് അറ്റ് റാൻഡം വിൽ കണ്ടെയ്ൻ 54 സൺഡേസ് എന്നാണ് ഞാൻ ചോദിച്ചതെന്ന് വിചാരിച്ചോ. 54 സൺഡേസ് എന്നാണ് എൻ്റെ ചോദ്യം എന്ന് വിചാരിക്കുമോ. അപ്പോൾ ഈ പ്രോബിലിറ്റി എന്തായി മാറി, പ്രോബിലിറ്റി ഓഫ് E1. അപ്പം എൻ്റെ ഈ പ്രോബിലിറ്റി എന്തായി മാറി, 0 വരുള്ളൂ. കാരണം ലീപ്പ് ഇയറിൽ മാക്സിമം 366 ഒബ്സർവേഷൻസേ ഉണ്ടാവാൻ പറ്റുള്ളൂ, അല്ലെങ്കിൽ ഡേറ്റ് മാത്രമേ ഉണ്ടാവാൻ പറ്റുള്ളൂ. അപ്പോൾ ഇത് വെച്ച് നോക്കുമ്പം ഇതെന്തായാലും ഇമ്പോസിബിൾ ഇവൻ്റ് ആണ്. അതുകൊണ്ട് അതിൻ്റെ പ്രോബിലിറ്റി എന്തായാലും 0 ആയി മാറി. ഓക്കെ, ഇങ്ങനെയാണ് നമുക്കൊരു ക്ലാസിക്കൽ ഡെഫിനിഷൻ ഓഫ് പ്രോബിലിറ്റീൻ്റെ എക്സാമ്പിളായിട്ട് പോകുന്നത്. ബേസിക് ഐഡിയ മനസ്സിലായി കാണുമെന്ന് വിചാരിക്കുന്നു. നമ്മൾ കൂടുതൽ ഇതിനെ പറ്റിയിട്ട് അറിയാമെന്നുള്ളത് മാത്രമേ ഉള്ളൂ. ഒന്ന് രണ്ട് ചോദ്യം കൂടി ചെയ്തിട്ട് നമുക്ക് എന്നാൽ ഇന്നത്തെ ക്ലാസ് നിർത്താം. അടുത്തൊരു ചോദ്യം വരുന്നത് among the digits 1 2 3 4 5 at first one is chosen and second selection is made among remaining four is made among remaining four, assuming all the selections are equally likely. Find the probability that an odd digit is selected. So here we have 1 2 3 4 5 as numbers. So if according to the question, if 5 is selected, then among 2 numbers has to be selected. Second selection is made. If first 5 is selected one, then we cannot take 5 once again. So these types of experiments will be called as simple random sampling or simple random experiments without replacement. Okay, so here we cannot take the sample once again, so it is called as without replacement cases. So it may be 5 1 5 2 like that, 5 3 5 4. These are only the permissible cases. Okay, so first of all we will find out what are the total number of cases here. So as a solution, what are the total number of cases? So let us write total number of cases are 1 2, one come with 2, one can come with 3, one can come with 4, one can come with 5, then 2 can come with 1, 2 can come with 3, 2 cannot come because 2 if selected at 1 it cannot be replaced once again. Okay, 2 4 2 5, so 3 1 3 2 3 4 3 5, 4 1 4 2 4 3 4 5, 5 1 5 2 5 3 5 4. These are the total number of cases. Okay, so how much cases are there? Total number of cases are 20. Okay, total number of cases 20. Total number of cases equal to 20. Now my first question is find the probability that an odd digit is selected. An odd digit is selected. odd digit is selected. So I rearrange the question is odd digit is selected. Here I can write it as for the first time the question is reshuffled, because we cannot find out how odd digit is selected. Total number odd means it is fine, but otherwise it doesn't have any meaning. Odd digit is selected for the first time, for the second time, okay, and both times we find out the probability for all the three cases. Okay, so if we case the first time, odd digit is selected for first time, so I make this as E1. Okay, so probability of E1 is total number of cases, number of favorable cases by total number of cases. So here favorable cases are what are the favorable cases? Odd digit is selected for the first time. So here it is odd: 1 2 1 3 1 4 1 5 3 1 3 2 3 4 3 5 5 1 5 2 5 3 5 4. Okay, these are the cases. So 1 2 3 4 5 6 7 8 9 10 11 12. So there are 12 cases. Probability of E1 is 12 cases divided by total number of cases, which is 20. Okay, 12 by 20 is the answer, or 6 by 10 or 3 by 5 is the answer. Okay, it's the basic idea. Next one. odd digit is selected for the second time. So odd digit is selected for the second time, so I call this as E2. Then favorable cases are so what are the favorable cases? Odd digit is selected for the second time. So here what happens? This is 1 3 is one case, 1 3. 1 5 is another case, 1 5. Then 2 1 2 3 2 5, 2 1 2 3 2 5, 2 3 2 5. Then here 3 1 3 5, 3 1 3 5, 3 1 3 5. Then 4 1 4 3 4 5, 4 1 4 3 4 5. Then 5 1 5 3, 5 1 5 3. So these are the favorable cases. So here we see that all the second items are even numbers. Okay, so there are 1 2 3 4 5 6 7 8 9 10 11 12 numbers. Probability of E2 is 12 divided by total number 20, then 3 by 5 is the answer. Okay, so next question: what if both are see, okay, both selected are odd numbers. So favorable cases are what are the favorable cases? Out of this we can write the favor, I call it as 3. Then favorable cases are both are odd. Okay, 1 3 both are odd, 1 5 both are odd. Then odd alla 2 lonu odd alla. Then 3 1 both are odd, 3 5 both are odd, 4 lilla 5 1 odd, 5 3 odd. Okay, so here probability of E3 is nothing but 6/20, or it is 3/10, or it is nothing but 0.3 is the answer for this question. Okay, so in this way we can find out for any value. Okay, suppose that I take another E4 as none is odd, no observation is odd, or no observation is odd. So I get E4 as 0 because either one of the observation is an odd observation. Okay, here, so total number of cases will be 0/20, so it will be 0. Okay, none is odd, so it will be 0/20. I think that the examples which we had discussed now is very much clear to you. Then in the next class we will be discussing about the examples related to cards ചീട്ടില്ലേ അതിനെ പറ്റിയിട്ട്. So what you have to do is that you have to make the notes for these 2 lectures. Then we can do some questions. നാളെ നോക്കട്ടെ, നാളെ ഓൺലൈനായിട്ട് എടുക്കണോ അല്ല ഓഫ്ലൈനായിട്ട് എടുക്കണോ നോക്കാം. എന്നിട്ട് അതിനനുസരിച്ചിട്ട് നമുക്ക് ഡിസൈഡ് ചെയ്തിട്ട് തീരുമാനിക്കാം. അല്ലെങ്കിൽ നാളെ 1-2 ക്വസ്റ്റ്യൻസ് ചെയ്യിപ്പിച്ചിട്ട് മറ്റന്നാൾ വേണമെങ്കിൽ ഓഫ്ലൈനായിട്ട് എടുക്കണം. അങ്ങനെ നിങ്ങളെ കൊണ്ട് ചെയ്യിപ്പിക്കണം, നിങ്ങളെ കൊണ്ട് ചെയ്യിപ്പിക്കാം. നോട്ട്സ് ആക്കി വെക്കുക, അതേപോലെ തന്നെ അത് അപ്ഡേറ്റ് ചെയ്യുക. ഞാൻ ഗൂഗിൾ ക്ലാസ് റൂമിൽ ആക്കിയിട്ടാകുമ്പോൾ ആ നോട്ട്സ് എല്ലാം സബ്മിറ്റ് ചെയ്യേണ്ടി വരും. ഏത് ദിവസമാണ് പറയാമെന്ന് പറയാൻ പറ്റില്ല. എല്ലാവരും ആ ദിവസം തന്നെ വീഡിയോ കണ്ടിട്ട് തന്നെ ചെയ്യുക, എന്നാൽ മാത്രമേ പ്രോപ്പറായിട്ട് മനസ്സിലാവുള്ളൂ. എന്തെങ്കിലും ഡൗട്ട് ഉണ്ടെങ്കിൽ ഗ്രൂപ്പിലിട്ടാൽ മതി, ഞാനതിന് ആൻസർ അടുത്ത ക്ലാസ്സിൽ തരാം. ഓക്കെ, സോ നമുക്ക് ഇന്ന് ഇവിടെ വെച്ചിട്ട് നിർത്താമെന്ന് തോന്നുന്നു. അപ്പോൾ താങ്ക് യു ഫോർ അറ്റൻഡിങ് ദ ക്ലാസ്. താങ്ക് യു എവരിവൺ. ഹലോ അല്ലേ.